Atoms are in all things, big and small. Today they are well understood, though there's a lot left to discover. But that wasn't the case until recently. To go all the way to the first contemplation of atoms means to travel to the Greeks in the 5th century BCE, before the Common Era. Called the laughing philosopher for how easily cheerful he was, here we see Democritus pondering. He asked how many times you can cut a substance. There could be an infinite amount of cuts, or as Democritus believed, you would reach a unit at which you could no longer divide. He called this unit atomos, the ancient Greek word for uncuttable. Democritus believed these atoms came in many different shapes, sizes, and masses, making up everything, even the soul, according to later philosophers like Epicurus. Many philosophers disagreed with Democritus, among them Aristotle, who believed everything was made out of the 4 elements: earth, air, fire, and water. This led Democritus to be discredited among the bulk of Greek philosophers. If only they knew, Democritus was on the right track. It took a long time for any advancements in the quantum world, but in 1804, John Dalton built upon the ideas of the ancient Greeks and came up with a more scientific definition of atoms, the atomic theory. He described them as indivisible particles that make up matter, suggesting that all matter was made up of these particles. Dalton helped give us somewhat of a definition of atoms, but not a complete explanation. Towards the end of the 19th century, physicist Joseph John Thomson discovered the electron by experimenting with cathode ray tubes. What are cathode ray tubes and how did the experiment work? Well, cathode ray tubes are vacuum-sealed tubes composed of a cathode, which is a negatively charged electrode, and an anode, which is a positively charged electrode. A high voltage is applied to the cathode, which frees electrons. The anode, which is positively charged, attracts the electrons, creating a beam. This beam can be further directed using an electromagnetic field and illuminated using a phosphorescent coating on the tube. In the experiment, Thomson placed a negative and positively charged metal plate around the cathode ray. He found that the particles emitted were attracted to the positively charged plate and repelled from the negatively charged plate, meaning the particles must be negatively charged. Further testing with different metal electrodes gave the same result. Using this evidence and finding the mass-to-charge ratio seen from the particles, Thomson concluded that the particles in the cathode ray were negatively charged, so small that they must be a part of the atom, and they could be found in all elements. The discovery of electrons showed that atoms were indeed divisible, necessitating a new atomic model, which Thomson created. Called the plum pudding model, though not by him, because it resembles the English dessert plum pudding, Thomson theorized that atoms were composed of electrons within a spread-out positive charge. Shortly after, in 1911, Ernest Rutherford took the stage. With a Nobel Prize under his belt, Rutherford experimented with alpha particles, helium nuclei created from the decay of radioactive isotopes. The Nobel Prize he won had to do with radioactivity and its decay, so there was nobody else better than him to work on this. Rutherford sent a thin beam of alpha particles at a sheet of gold surrounded by a wall that would flash from collisions with the alpha particles. If Thomson's plum pudding model had been correct, the particles would have gone through the sheet because the positive charge in the atom was supposed to be spread out and therefore have too weak of an electric field to affect the path of the alpha particles. However, the alpha particles did not behave as expected. While most alpha particles passed through, the ones that did not were deflected over 90 degrees from their path. Rutherford, enthusiastic about what this could mean, said it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back to hit you. He theorized that the positive charge was not diffused and instead in a small volume of the atom. This positively charged part of the gold foil atoms and alpha particles must have collided, rarely as seen in the experiment, repelling the alpha particles. On the other hand, since most of the particles went through, there must be a lot of space in the atom. Following what he had observed, he recreated the atomic model in which the nucleus had a positively charged particle named the proton, Greek for first, with negatively charged electrons orbiting the nucleus. The atomic model is beginning to look like the present-day model. However, seeing how oppositely charged objects attract each other, what didn't make sense was why the electrons didn't spiral into the protons. When Niels Bohr came into the picture in 1913, he reasoned that there were energy levels, or shells, in which electrons would have to stay but could move throughout when enough energy was gained or lost. Why couldn't these electrons lose energy and spiral in? Because electrons in stable orbits don't emit radiation and therefore don't lose energy and can't spiral inward. With the development in quantum mechanics in the 1920s and 30s, these discoveries began to speed up. Our understanding of the atomic model began to change. The Heisenberg uncertainty principle states that we can't know the exact position and momentum of a particle such as an electron simultaneously. Viewing means having light hit the particle and be reflected, which would give the particle energy and cause it to move. This brought clouds of probability into the atomic model, areas where the electron could be, with varying chances in specific locations dependent on the energy that the electron carries. This model, though much more accurate than the earlier models, is not taught in schools, maybe because it's too complicated to understand. I think, however, that we should teach this model in classes. There is one key ingredient of the atom that we didn't have until 1932, the neutron, discovered by James Chadwick. The neutron is responsible for the stability or instability of the atom. Depending on the number of neutrons in the nucleus, you can have a radioactive atom, which is, I think, pretty sick. At this point, we have the classical school-taught version of the atomic model. But wait, the nucleus can be further divided. Though there were discoveries of other subatomic particles, one of the most significant was the discovery of quarks in 1964 by Gell-Mann and George Zweig. There are different types or flavors of quarks: up, down, charm, strange, top, and bottom. Understanding quarks was fundamental to understanding particle physics. Okay, so we started 2,400 years ago with the Greeks, who theorized that you could either cut something infinitely or would reach a point at which you couldn't. We then accelerated to 1804, where Dalton created the atomic theory. Then we zoomed into 1897, when Thomson discovered the electron and created the plum pudding model. We walked through 1911 to Rutherford with his game-changing discovery of the proton and orbiting electrons. We then entered Niels Bohr, who introduced quantum levels to explain why electrons don't spiral inward. We saw a change from this clean, determinable atomic model to a model where the realm of uncertainty took charge. With the discovery of neutrons, the atom felt complete, but a closer look into the particles revealed many, many more particles, among which were the quarks. Today, we believe that 17 fundamental particles, with more possible, make up the world. So, to answer the 2 millennia long question, how many times can you cut something? Turns out that there's indeed a point at which you can no longer cut. However, even that may be cuttable. Whenever that day comes, you can trust that I'll fill you in. So, please like and subscribe, and I'll see you in the next one.